Good morning, and thank you for joining us. So we're just waiting for participants to come online, so just stand by and we'll be starting momentarily. Good morning, and welcome to webinar number 5 of the AHRI Refrigerant webinar series, Refrigerant Ignition and Open Flame, Hot Surfaces, and trying to focus on the question, has anything fundamentally changed? On the next slide, we're just going to introduce our speakers today. So Dr. Tom Lewandowski is a toxicologist and chemist working in Gradient's Seattle, Washington office. He has over 30 years of experience in the area of product safety evaluation, including the evaluation of new low global warming potential refrigerants. He's a member of the OR's Wheel Committee, which reviews toxicology data to develop workplace exposure guidelines for new chemical agents. Steve Kuyak is the director of next generation refrigerant research for Trane Technologies. Over the past 28 years, he has led and been involved in numerous technology and product development projects, including development of new refrigerants, lubricants, and compatibility of system materials. Steve has been an author or co-author on more than 50 publications related to refrigerants and has 19 patents related to the HVAC products. He's the chair of AHRI Standard 34 Designation and Safety Classification of Refrigerants. Mary Coban works for the Chemours Company and has worked on low GWP global warming potential refrigerants since 2006. She has been involved in many of the AHRI-TI, the Technical Institute's research projects regarding flammable refrigerants. She's a member of ASHRAE 34, ISO 817, along with several international standards. Her expertise is refrigerant flammability, safety, and use with various publications in those areas. George Hunter, who we heard from also on our first webinar series, is an engineer with UL's Research and Development Organization. He has been the lead investigator in AHRI's 9007-1 and -2 projects dealing with flammable refrigerants. He's currently leading AHRI Project 8028, A12 refrigerants and firefighter tactical considerations. Thank you all for joining us today and welcome, and we look forward to discussing these issues with you as we go forward. We have repurposed a slide that Dr. Lewandowski put together, just some thoughts to remember and to think about as we're walking through these presentations. There is no risk of HF generation and exposure under normal operating conditions of an air conditioning system. We're looking at rare, accidental, and acute exposures. All fluorocarbons produce hydrogen fluoride, carbonyl fluoride, and other highly irritating and toxic gases via thermal degradation. And personal protective equipment and best maintenance practices should be used to minimize and eliminate exposure to refrigerants and their combustion products. And you can go to the next slide. Thank you, Shadon. And with that, I'm going to ask Mary to provide us some information around refrigerant combustion and thermal decomposition, kind of giving us her broad background around research that was done not only for the air conditioning and refrigeration industry, but also research that was done for the automobile industry as they were required to transition earlier, especially in Europe 10 years ago. Thank you, Mary.
Oh, hey, good morning, and thank you for having me here today. Today I'd like to discuss the automotive industry journey and our learnings. And as Helen said, I have 2 feet in this industry. I have 1 foot firmly planted in the automotive and 1 foot firmly planted in the stationary side. So today I'd like to review with you our automotive industry learnings. What was that journey? Some of the things we looked at: key refrigerant breakdown processes, combustion and thermal decomposition and, the product of significance that we looked at for that. And then I'd like to get into the relative amount of those byproducts, what we found when we did different types of tests, lab environment tests or semi-lab test environments, and then real-world scenarios, and try and go and connect to some of the other information that was shared with us by earlier participants on hot surface ignition testing. Next slide, please. Let's discuss the automotive journey and the industry regulatory drivers. I know some of you folks probably are well aware of this. In 2006, we had the European MAC directive, and it required that mobile air conditioning AC refrigerant use a refrigerant with a direct GWP of 150. And this was implemented in 3 phases from 2008. With full EU industry engagement by 2017. And what it did was, starting in 2011, all new platform model vehicles had to use a low GWP refrigerant or GWP less than 150. And by 2017, a low GWP refrigerant was required in all new cars. The United States at the same time had some similar regulations coming along, although not on a mandate. We had what we called an incentivized program, where we had a corporate fleet average fuel economy of less than 250 gram per mile of CO2, and low GWP refrigerant could be used towards the CO2 requirement, and automotive OEMs could gain CO2 credit by using a low GWP refrigerant. Next slide, please. As we talked about it, the automotive industry was on this journey. And similar to what we're doing with AHRI and Ashrae, the automotive industry through SAE International looked at the forefront of these regulations back in 2006, and actually even earlier, but in 2006 we saw this coming along. Therefore, in 2007, technical experts from the global automotive industry, manufacturers, suppliers, independent test labs, initiated the SAE Cooperative Research Program. We call that the SAE CRP 1234. Again, to investigate safety and performance of 1234YF for use in mobile air conditioning. Under that work, there were 3 risk assessments completed as part of that work, and I'm happy to say we had gradient again. Dr. Lewandowski was part of that work, and it was great. And if you look here, you'll see that at that time, we had all the brands that were shown there were represented, and that was about 70% of the vehicle, light-duty vehicle market. Next slide, please. So what do we take out of this? What was the first thing that we looked at? Well, we looked at this and we said, well, refrigerants are really stable under normal HVAC use, right? Or automotive air conditioning or stationary air conditioning use. However, when refrigerants escape into the environment, they eventually break down. If refrigerants are accidentally released into the environment, no fire, no heat, just released from a hose line or system failure or accidental release by a technician, they typically decompose according to their atmospheric lifetime. They go into the stratosphere, troposphere, and they just degrade. And what you can see here, the reason why folks are very interested in low GWP refrigerants is they have a very low, typically a low atmospheric lifetime too. So 134A has an atmospheric lifetime of 13 years. 1234YF has an atmospheric lifetime of about 11 to 12 days. Now, if refrigerants are accidentally released into a fire or hit a hot surface, slightly different breakdown products can be formed right then, typically HF. Now, before we get into the decomposition products, let's talk a little bit about some basic definitions. Fire is the rapid oxidation of a material through the chemical process of combustion, releasing heat, light, and various reaction products. Combustion is the chemical process, especially oxidation, accompanied by heat and light. Flame propagation, and I know through these series we've had a lot of discussion about flame propagation. Flame propagation is the movement and spread of a flame outward from the point of combustion or ignition, right? I think what's really important here, and it's very key, is that all HFCs can combust if the ignition source is of sufficient energy. I think that's really important for people to look at and think about. And what we also have discussed a lot through this seminar series is that per the Ashrae definition, class 2L, 2, and 3 materials exhibit flame propagation. Again, Ashrae class 2L, 2, and 3 gases are such that when they're mixed in the appropriate amount, that's between the LFL, the lower flammability limit, and the upper flammability limit, they'll propagate a flame when subject to an ignition source of sufficient energy. And that's our standard test that we use in Ashrae, Ashrae Standard 34. Now let's switch gears and just touch one bit upon a possible decomposition product. So the possible product that most folks are looking at is hydrogen fluoride. Hydrogen fluoride can be formed when fluorine-containing refrigerants are exposed to an open flame, that's our combustion, or an extremely hot surface, that's our hot surface temperature. Again, this holds for A1 refrigerants also. The amount of HF, though, that's generated by combustion, and that's what I'm going to share with you, this was our big learning in the automotive industry, is really dependent on the amount of refrigerant that gets within the combustion zone. It's also very interesting to note that HF exhibits initial warning signs of about 2 to 3 ppm. So as soon as there's 2 to 3 ppm, you can start to smell it and you feel irritation in your nose and walk away from the HF. Both HF and HN acid can be formed during potential failure events, a line break, an accident, when exposed to high temperature or an ignition source. The other thing to think about is HF is a very light molecule and has a tendency to quickly rise in the air. HF acid can form on surfaces where moisture is present. The reason I want to share that with folks is I think sometimes folks confuse HF and HF acid. Next slide, please. Now, let's go back and discuss combustion a little bit more. What do we mean by combustion? Again, complete combustion rarely takes place. Complete combustion is kind of difficult to achieve. Refrigerant is a gas and expands quickly when liberated from an HVAC or an MVAC system. And the highest probability of complete combustion, again, in this fire type event is occurring is very difficult, right? Why is it difficult? What we see is when we have a release, we're not in this area where we're well mixed, non-flowing, and in the presence of ignition source. What we see is when we have partial combustion, we don't have that, right? So from our SAE CRP work, we always assumed we had the worst case scenario. We always assumed we had complete combustion or complete conversion of refrigerant to the decomposition products. We also assumed in this work that we did that we always had HF. Why did we do that? Well, we noted that as soon as we had a little bit of moisture there, COF2, which is another decomposition product, quickly converted to HF. Next slide, please. So let's go back and talk about complete combustion. Again, we mentioned complete combustion is difficult to achieve. If I look at 134A and I look at the equations for combustion, just trying to share this with you folks, that 1 mole of 134A produces 4 moles of HF, and on a kg basis, we get 784 grams of HF. Right? Now let's look at 1234YF. Again, here's the equations for complete combustion. I don't want to bore you with the details of the chemistry, but you'll see 1 mole of 1234YF combusted also produces 4 moles of HF. However, on a kg basis, we see that we really only get 702 grams of HF. Now, this is showing us that on a complete combustion scenario, 134A can actually generate more HF than 1234YF. The other thing, though, to really think about, though, is combustion reactions have the potential to form HF. What we found is in the HVAC and MVAC industries, we've been working with 134A for over 25 years without a known HF incident. And in the MVAC industry, we've been using YF for 9 years. Again, we talked about the introduction being 2011, and we're estimating that there's 70 to 100 million vehicles on the road today without any incident. Now let's go back and look at the really interesting scenario, which is much more likely to happen, is partial combustion. In this type of scenario, what you can see here, and I've done a little diagram for you folks to look at, is you can see a line where you have refrigerant that's leaking out of some kind of a line, and it passes over a flame or a pilot pipe, and you can see there's this cone, and you can see the area that passes over the flame or near it. And that's the area that's really subject to breakdown. So what you can see is partial combustion is expected and seen in many, many cases. In experimental tests, flame propagation for A2L refrigerants was not really observed when the air was static. That means, like, if we had an ignition source and we just released the refrigerant, and it was a high velocity release from like a leaking line and went over a little flame, half of the time it would extinguish. And that's actually some of the information that the UL team shared with us in the earlier AHRTI project, I want to say 9015. Very interesting information there, right? Let's go on and look a little bit more at partial combustion. And what we see, partial combustion kind of results in only one fluorine atom being removed from 1234YF. This generates only 1 mole of HF versus 4 mole of HF. So that's why under these partial combustion situations, we're expecting to see a lot less HF formed, right? And partial combustion is more representative of many of the scenarios we're used to seeing. Why? Well, we have poor refrigerant and air mixing, right? The refrigerant is leased into an area and it's not fully mixing. There's dynamic flow, meaning the refrigerant gets a chance to move out from the line. The refrigerant leak is before or after an ignition source, right? How often do we have those happening? The volume for the refrigerant to move away from the flame source is larger, right? You know, the refrigerant isn't right beside where the ignition source can be. And that's why more realistic scenarios produce significantly less HF than idealized laboratory well-mixed scenarios, right? And that's kind of the combustion points. Now, let's go back and look at hot surfaces. And in the automotive industry, why did we start thinking about hot surfaces? Well, I think there was a really important point looking at, again, looking at our standards, looking at the stationary standards. What did we think about? Typically, the industry looked at AIT, auto ignition phenomena, right? In auto ignition phenomena, that's when a refrigerant spontaneously ignites without an external ignition source, right? In that test, and the test that's done, AIT test, refrigerant is introduced into a beaker inside an oven, and the temperature is increased until spontaneous ignition occurs. And that's very interesting, but it's very, very static, and the refrigerant is contained. And it's not really kind of what we're going to see in our systems or in our vehicles or in the front end of an engine. So we started looking at HSIT, or hot surface ignition temperatures. And there were 3 that were looked at during the time of the SAE work. And I just want to share these with you. We looked at a hot rod, the one here on the left, that is looking at a simulated exhaust manifold that we find underneath the engine. We looked at a heating element, again, trying to get some very hot temperatures, again, that we would find underneath the engine hood. And then we looked at a flat plate. Each of these were done. Different groups did this work. And these were all useful and provided us information on hot surface ignition temperatures. And we looked at these in the MVAC industry. Next slide, please. So now going to this point, why is thermal decomposition important in a hot surface? Well, hot surfaces can lead to thermal breakdown and decomposition too. And this is what we kind of felt we had more happening in the automotive industry, right? We had thermal decomposition caused by heat. This is a reaction that is endothermic, as it's required to break down the chemical bonds in the compound before you can actually decompose them, right? So in our work for SAE, we were really interested in the thermal decomposition that occurs when refrigerants impinge on a surface that's hot enough to excite fluorine atom to break away. Right, so we really wanted to understand what that was like. We started looking at this, and our team also developed some hot surface testing methods. Next slide, please. One of the things I thought we should look at before we start looking at the raw data, and I think Dick Lord and some other folks shared this in earlier presentations, is that we need to look at how the refrigerant cools the surface. And we actually did that. So what we did was we looked at hot surface testing. I showed you the planchette on the earlier slide. We had that up to some instrumentation. We were able to measure the surface temperature. So what we did was we released refrigerant on a hot surface, and within 5 seconds after the release, the surface temperature decreased. And what we saw was it took about 30 seconds on average for the hot surface to come back up to temperature and plateau. And during that time, we found no ignitions in that testing up to 800 degrees C. Similar results were found by Carrier. We also found the same thing with Project AHRI 9008, which also included oil. So just to kind of give you some data on that. So again, let's talk a little bit about what impacts the thermal decomposition, and then we're going to go and look at some testing that we did in the automotive world. Again, very similar concepts, thermal decomposition to combustion, but I think the important point here now is what's really important and what impacts thermal decomposition is the temperature of the hot surface. You know, how hot is that surface? How long is it hot? The size and the geometry of the hot surface. I showed you the long rod, the flat plate, cylinders. The amount of refrigerant that hits that surface. Again, not all refrigerant hits the hot surface during a release. And the time of contact with the hot surface, right? So if the refrigerant comes out and immediately cools the surface and more refrigerant comes out, you're really taking away time for the thermal decomposition because the surface is cool now, right? And again, thinking about what do we really have in the real world, most refrigerant leaks occur very quickly within a relatively short time and contact with a hot surface. In addition, unlike the AIT test, in the hot surface and what we see in real world, the refrigerant is free to dissipate to the surrounding area, so the amount that hits the surface is also less. Therefore, it's pretty difficult to decompose refrigerant during these short random leak events. But now let's go and look at some data and some tests that we did at SAE. Again, this test was done at one of our third-party labs, Interis, another safety expert. They're located in France. What we did here was we looked at thermal decomposition tests, and we looked at a simulated vehicle exhaust manifold. If you look to the picture on the right, that big rod is our exhaust manifold that you would think would be in a car. If you look to the left, you can see blocks simulating a highly packed engine. We purposefully put in a lot of blocks and everything to give us about a 40% packing rate. I know we've had discussions about, you know, how does that impact, you know, tests? Well, we did that in the automotive world. And here's what we found, the effect of the hot body and temperature and surface temperature. We found in general that the amount of HF generated during thermal decomposition from this test was highly dependent on the temperature of the hot body, right? We also found that when we changed the surface area of the hot body from 1400 to 35 square centimeters, the concentration of HF formed decreased by 40-fold. So again, if we have an enormous hot surface, you can see that you're going to get more HF generation. If you have a smaller hot surface and smaller contact time, you get less you get less generation of HF. And oil, we found, really does not change the ignition temperature, but reduces the time to the ignition event. And that was, I want to put a disclaimer in there, that was for these tests. And that was our level of oil that we used in the automotive world. Next slide, please. The other thing I think we found that was really interesting is that in this test right here, and this was in a, if you look at it, was in a box and everything, so the refrigerant was released in there, released on the hot surface, and allowed to move around. What we found is that 1234YF did not have any ignition at temperatures up to 1000 C. We found that the oil generally has an ignition. Oil itself on a hot surface has an ignition of about 200, 250 C. Oil reduces the ignition temperature of 1234YF, or more appropriately said, the refrigerant increases the ignition temperature of the oil. Oil on its own would ignite at a much lower temperature, right? The leak geometry, we also found that when refrigerant was sprayed at or near the hot surface rather than directly on, the amount of HF was decreased by about 15 to 35%. And again, I think, you know, that's some of our learnings, you know, from this testing. Next slide, please. Now let's talk a little bit about the next level of tests that we did. We started out with lab testing, then we went to a test vehicle. And when we went to the test vehicle, what did we find, right? Vehicle OEM spotted some testing at Hughes Associates to evaluate potential HF generation via thermal decomposition. And we went and released refrigerant into an engine compartment onto a hot surface at temperatures below the ignition temperature. And we varied the hood up and down and closed, and with the AC fan on and off. And we also went and made some more idealized you know, experiments to this. We went and took the seals off of the flaps that lead into the ductwork into the passenger compartment so that HF gas could egress into the passenger compartment, right? We took HF and HF acid samples in various locations. Next slide, please. And here's what we found. So again, looking at this, you can see some of the levels of HF that we found in the driver's breathing zone. So again, these were tests that were done to generate thermal decomposition in the engine compartment, hood up or down, fan on or off, seals compromised or open so that we could have any HF that was formed in the engine compartment travel into the passenger compartment. And then we looked at what would be in the passenger's breathing range, right near the nose area. And we looked at that for a 3-minute average. This is just some of the data. There's more in the report, but this is what you can see. And you can actually see we have 134A has an HF concentration of about 1.7%, and YF, you could see where we're at there. And you could see the ppm. You could see the ppm over on the right-hand column, 0.98, 1.69, again, lower levels in the breathing range. Next slide, please. Then our final thing that I wanted to share with you is the simulated crash vehicle done by KBA, the German Federal Motor Authority. In this, we compared a worst case simulated crashed vehicle. Then we went and took these parts and they were put back together. And again, some thermal decomposition tests were done from this in the engine compartment at 700 degrees. And what we found here was similar amounts of HF formed during failure events for 134A and 1234YF. What we found was about 3 ppm of 3 ppm of 134A, excuse me, and 3.57 ppm of 1234YF. So last slide, please. So overall in our testing observations, what do we find? In lab testing for decomposition, what do we find? Lab tests are ideal. They generate the worst possible case, and they're designed to get large amounts of decomposition products, right? So we've got idealized situations where it's boxes that are enclosed and we're gathering information, larger pieces of equipment, larger periods of time, the refrigerant really isn't able to move. Then we start going into, again in SAE, we started going into more realistic vehicle testing, right, for decomposition products. Less decomposition products are formed. The refrigerant is more realistically able to escape even into the local environment. And even though that local environment is very packed under the hood, the refrigerant is able to escape. We see less HF is formed. And then we go even further to where we actually go and simulated crash vehicles. And we did testing again for decomposition products. And we found even less decomposition products are formed again as contact time and dynamics reduce the refrigerant decomposition. So what do we find? Refrigerants are gases which move away from hot surfaces. And then in the real world, we find that as the amount of HF is formed is typically low because of some of the real world environment around it, right? But what I would leave you with is that the key has been for the industry to follow the safety guidelines and follow correct service procedures and PPE, and everything will be work out. As we have found in the MVAC industry, it has been safely working with 134A for over 25 years, and we've been safely working with 1234YF for over 9 years, with an estimated 70 to 100 million cars on the road. And I think that's it. And on the next slide, I think I gave everyone some references. In case anyone had any questions or anything later, they can go look at some references too.
Thank you, Mary. Really appreciate that summary. Now we're going to turn our attention to Steve Kriak, who's going to introduce the project at AHRI RP 1855, the determination of the impact of combustion byproducts on the safe use of flammable fluorinated refrigerants. Steve, thank you very much.
Yes, thank you. So I'm going to spend a little time introducing this project that AHRI has been running. Tom Lewandowski will follow right after me, who is the principal investigator on this project, and will bring people up to speed on what the findings have been. The project is nearly complete, at least phase one of this project is nearly complete. And so Tom will present information that'll be going into a final summary report here the next month. So members, got together, and we've been, doing all these research projects around different impacts, and Mary did a nice job, looking at hot surfaces, and obviously there is a lot of difference on hot surfaces between flammable refrigerants and what we consider class 1 refrigerants. But if we do get a combustion event, in this case, we wanted to look at what is the state of the art on combustion byproducts, the safe use of flammable refrigerants. So next slide, please. Go back a slide, I'm sorry, I'm looking at my screen. So the project is divided in 2 phases. So phase 1 would be, or excuse me, phase 2 would be experimental work if knowledge gaps are identified in phase 1. So the phase 1 objectives were, clarify the decomposition products for these refrigerants, and understand any consequences associated with combustion events, and potential health impacts if you're exposed either dermally or from gas. And then collect and generate basic data to support industry risk assessment. So a lot of people have done a lot of toxicological work around HF in different situations. So we wanted to be able to look at those to see if there is any necessary steps that need to be improved safety. So next slide, please. So phase 1 is very general. We're doing a literature surveys, to summarize existing fluorinated refrigerant risk assessments around HF and carbonyl fluoride formation. And then we're doing literature survey around the byproducts for fluorinated or previous refrigerants exposed to flames or hot surfaces as well. So there's a large data out there on all these different things. We want to pull those all together. And then on phase 2, we want to propose a plan, around, if we do a combustion event, how much HF, carbonyl fluoride forms during a thermal decomposition or combustion event, and does the amounts differ? And what are the recovery actions, if we have an event? What happens to these byproducts, once they form, you know, after the combustion, do they plate out on surfaces? How long do they persist? And what precautions do need to be taken for first responders or other entering a room after an ignition event? You know, the equipment and the standards are designed not to have an event, and it's very rare, but what if one would have happened? What is the concerns and what do we have to approach this? So, you know, the final thing is, what is a minimum event that's considered dangerous? And does a torch near a class A2L refrigerant create a situation much different than a class 1 refrigerant? And what is the magnitude of the ignition event size after the danger? Is there a threshold around concern? So can we, if it's small amounts of material generated and it's more than what an A1 does today, how significant is that? So that's an introduction to 1855. And like I said, we're just completing up phase 1. And then we'll be working toward phase 2 in the rest of the year and next year. So Helen, we can move on to Tom.
Thank you, Tom.
Steve. Oh, thanks, Steve, for that introduction. So nice to be here today. I did just want to mention that this project is currently still in progress. We are wrapping it up, but it's not completed. So I can't actually share the conclusions. That's part of AHRI's requirement, but I can certainly share some of the things that we've seen and some of the data we gathered. So again, happy to be here today to sort of share what we've seen so far. So, you know, there is a concern, and there'll be some of this we'll be repeating from what Mary said on some level, but there is a concern about fluorocarbon decomposition products. And that's, you know, again, because we're transitioning from the CFC and HCFC world to these A2L refrigerants. As Mary also suggested, we're not really talking about a novel risk here, right? Because some of these quote unquote non-flammable refrigerants can combust and produce degradation products when they're exposed to fires. It's really a matter of frequency and quantity. So, you know, do these new refrigerants have greater potential to ignite? Is it more likely, because of their potential flammability, that we would have some sort of decomposition event? So these are the things we need to think about. But again, it's not really a new risk overall. And as Mary also suggested, the principal fluorocarbon decomposition product is hydrogen fluoride. And that's a highly corrosive and irritating gas. I'll say a little bit more about that in a minute, but it certainly does present a hazard that we would want to be concerned about. As was also discussed, there's also carbonyl fluoride, or COF2, and that can be produced as well, but it will hydrolyze to HF. For example, in the sort of wet linings of the respiratory tract, for example, you'll have COF2 being converted to HF if it hasn't already been converted by atmospheric moisture. And again, you know, a lot of the information we have comes from the automotive sector. That was a multi-year investigation, and certainly the automotive and stationary sectors have important differences, but the work that was already done in the automotive sector kind of gives us a leg up and really gives us some useful information to then carry out new studies that would be relative to the stationary sector. And in fact, that has been done to some extent. Next slide. So just a little bit about our literature search approach. So I really do think of this project as kind of a, what is the state of knowledge sort of investigation? You know, what do we know and what are the important data gaps? So we did a large number of database searches, looking at a large number of different databases, you know, Google Scholar and PubMed and NIST publications. And I'm not going to go through all the keywords we used, but, you know, we used a fairly broad net to try to really understand, you know, the properties of refrigerants and why they might decompose and under what conditions, how much HF or COF2 might be generated. You know, we also looked at some fire suppression studies because those agents obviously are related, and those have been looked at quite a bit. And then we obviously wanted to look at health effects, both from inhalation and dermal exposure, and then also potential ways to mitigate some of the residues that might be formed. So, you know, we ended up with, gosh, it was probably over 700 citations that we looked at to see if they were relevant, and then sort of winnowed that down to a more reasonable number of relevant articles to then develop the report based upon. Next slide. So just a little bit about some health effects information we gathered. So, you know, HF is highly irritating to the airways, and at sufficient time and concentration, and that's important, it can cause the destruction of the airways and edema or sort of buildup of fluids and potentially death. But again, it's at sufficient time and concentration. So there is a certain importance to those factors. Data in humans are actually fairly limited, as you might imagine. There are some case reports, so these are very limited studies of workers who've been exposed. And in particular, there's one interesting case report about workers who were exposed to a refrigerant leak in a kitchen. So these are actually kitchen workers, not necessarily repair workers, but there was a refrigerant leak in the kitchen and there was an active gas burner. So some decomposition products were formed. I should say this was not with an A2L, this was with an A1 refrigerant. And the workers were not wearing PPE. There was, as typical for a lot of these case reports, no concentration data. So we don't actually know what they were exposed to in terms of levels. We just know that based upon some of the health effects seen, they probably were exposed to HF as well as potentially hydrochloric acid from the CFC. And then several of these individuals, did have respiratory problems, but recovered over several months. 3 of them did have lingering problems, sort of respiratory decrements, right, that were non-life-threatening. And those did linger for at least 4 months, but were being treated by corticosteroids, so inhalers. So again, very few case reports out there, but some useful information. And then in terms of sort of more experimental studies, we know that people can be exposed to 3 ppm to HF for an hour and really experience no adverse clinical effects. So maybe some irritation, but nothing more significant than that. And then we have studies in animals. So that actually can be quite useful. We know that there are studies in rats where they've been exposed to 950 parts per million of HF for 10 minutes, and they basically had no adverse effects. And that study was actually used to derive some exposure limits, which I'll talk about in a few slides. And then similarly, there are studies in dogs who were exposed to 243 parts per million for 1 hour and only had moderate eye and nasal irritation. So I think, as Steve alluded to, there have been some toxicological studies done, and those were reviewed and summarized in the report in terms of what they might mean for potential exposure. Now, dermal exposure is also a concern, right? Because if you have a thermal decomposition event, there could be some residues deposited on surfaces, as Mary suggested. And HF is an unusual molecule in that, unlike other acids like hydrochloric acid, it doesn't dissociate perfectly, right? There's some HF that is still present without that dissociated hydrogen, and that non-dissociated HF can penetrate through the skin and reach the tissues. And so that's a sort of an added concern about HF. And so that undissociated HF can damage tissues, particularly the bone, because HF likes to bind with calcium. And at substantial exposures, so we're talking here about severe burns from highly concentrated solutions, so like 70% solutions, you can have cardiac effects, right? Because it gets into the systemic circulation and can affect calcium there. But again, only from very high intensity burns from concentrated solutions. So the reports from the toxicity of dermal contact primarily come from individuals using concentrated hydrofluoric acid solution. So it's things like tire rim cleaners in the high percentage range. So 20, 70%, really, really high levels. There's no indication that lower concentrations, like perhaps less than 0.1%, produce such effects. And I'll come back to that point when I talk about some of the automotive work and the levels seen from some of those releases. And it's also true that HF reacts rapidly with surfaces. Again, it's a highly reactive molecule, so that's going to limit the exposure time, right? Certainly it also may volatilize from that moisture and sort of reduce things as well there. So again, HF should not persist for a very long time. Nonetheless, emergency response and cleanup personnel really should be wearing PPE. That means respirators and gloves. The type of glove really depends on the strength of the solution. Nitrile gloves may be appropriate for low concentrations, for example. And as with all chemicals, the exposure concentration, that is the dose, is really the key to understanding the health risk. Next slide. So a little bit about exposure limits for HF, because some people may be aware of these. There are some chronic exposure limits. So there's, for example, under OSHA, the Occupational Safety and Health Administration, an 8-hour permissible exposure limit of 3 parts per million. NIOSH, the National Institute for Occupational Safety and Health, has a similar 3-hour or 3 ppm 8-hour limit. They also have a ceiling limit of 6 parts per million, and that applies for 15 minutes of exposure. The important thing to note about these, though, is that these are both for repeated exposures. So something you could be exposed to every single day of your working career. They're really not appropriate for accidental releases, which might happen, once or twice, right, in a person's lifetime. So those values really wouldn't apply to an emergency situation, an accidental situation. What may be more appropriate is the acute exposure guideline level, or the EAGLE, which is really meant for sort of emergency exposures. And there is an EAGLE value set by the US EPA of 95 parts per million for 10 minutes for HF. And that's, again, based on that rat study I mentioned, the one that involved 950 ppm exposures. And then that was divided by a value of 10 for additional safety. And in fact, this EAGLE value of 95 parts per million was what was used as kind of the health-based limit in the automotive risk assessment. I also did want to mention, again, because I think it's relevant to exposure concerns, that HF does have a very low odor threshold, so it's actually somewhat lower than the value that Mary gave. It's 0.02 to 0.13 parts per million when you can actually sort of detect the pungent smell of HF. Now, at about 3 parts per million, you'll actually have significant irritation. But therefore, unlike some other chemicals like carbon monoxide, HF actually does have a pretty good warning signal. And so once you sort of detect that, you're likely to move away because it's a very irritating effect. Next slide. So that's a little bit about health effects. So what kind of HF exposures are possible, right? So let's look at that for a bit. Next slide. So we did look at studies involving fire suppression agents. So again, many decades of work have really been devoted to understanding what happens when a fluorinated fire suppression agent comes in contact with a fire. And so large number of studies, on various HFCs, again, no A2Ls though. And these are sort of room scale studies that were done, and they really did show large amounts of HF being generated, thousands to tens of thousands of ppm. However, these studies are really difficult to interpret in the context of A2L use in sort of an HVAC application, because the studies really most of them involved really high energy fires. So burning pools of heptane and large amounts of suppression agent being put onto the fire and near complete decomposition of the agent, right? So Mary talked about kind of the importance of understanding how much is actually being decomposed. And studies of less energetic fires, so again, not heptane pool fires, but paper and office equipment fires, for example, showed substantially lower HF concentrations. So the peak concentrations, the maximum concentrations, were tens to hundreds of ppm, so several orders of magnitude less, right? And again, no studies of A2Ls, so again, we're trying to sort of infer from this data what we might see in an A2L situation. So overall, these fire suppression studies indicate that there's a hazard, but they don't indicate the risk. And these are kind of important terms that I like to sort of use. A hazard really indicates whether something can occur under some conditions, right? So is there a potential concern there? Whereas a risk really focuses on the likelihood the effect occurs under specific conditions. So these studies really tell us that yes, there is a hazard, but because of the difference in sort of situations, they really can't tell us about the risk. So next slide. So the automotive studies that were done really can give us more insight about the potential risks. And again, Mary talked about these, so I won't go into the same level of depth, but I will talk about some of the higher level findings in the context of exposure. Again, it was a broad industry-wide effort, and there was extensive bench scale, vehicle scale, and modeling work really done to explore kind of what levels of HF and COF2 might be generated. Next slide. So I did want to focus on some of the field studies. Again, Mary did talk about this briefly. I'll give a couple other details. So again, basically these were releases of refrigerant onto a hot surface. Charges range from 600 to 1,000 grams. There were a number of things that were done to make this kind of a worst case situation. So the hot surface was placed near the top of the engine compartment, so like not down where the manifold would be. That's closest to where the driver might be. It was the 1234YF was released directly onto the hot surface, so kind of a worst case orientation. There was also no wind, and they had the AC system on, pulling air from the engine compartment into the cabin, which again would not be a realistic situation. There would be shut-off mechanisms, for example. And they measured HF at various locations, both in terms of air concentrations and surface concentrations. So some wipe samples or little deposition containers were actually put at various locations to measure how much HF would be deposited on those surfaces. So what did they find? Well, the highest HF concentration in the passenger cabin was basically 35 parts per million. That's as a 3-minute time-weighted average, right? That was the highest concentration. All the other results were below 10 parts per million. And those are below the 10-minute acute emergency guideline level, the EAGLE value of 95 ppm that we just talked about. So again, no exposures at levels of concern. The highest concentration in the engine compartment was 119 parts per million. So again, that was when they had an apparent ignition event, and that's above the EAGLE, although not very much higher. But again, you wouldn't expect an individual to be present in the engine compartment, so limited risk there. In addition, the surface deposition concentrations that were measured were actually quite small, less than a microgram per centimeter squared, which is well below 0.01% concentration. So again, we wouldn't really expect an exposure that would be of concern from a dermal standpoint. I did also want to mention some modeling that was done. So essentially, based upon the bench scale work, a model was created that would then allow for prediction of HF concentrations in an engine compartment. And so the idea was to use this model and sort of see if it could predict what was seen in some of those field tests. And in fact, the model was able to match the field test results when there was adjustment for the efficiency of decomposition. So again, as Mary alluded to, if the refrigerant is sort of passing quickly across the hot surface, it's not going to acquire enough energy to completely decompose, right? So that had to be accounted for. And what's shown in the graph here is just the blue line indicates the refrigerant concentration. The red line indicates the HF concentration, and these are the predicted values. So the refrigerant time-weighted average is 1.8%. The HF time-weighted average is 13%. And in an analogous field study, we ended up with refrigerant concentrations of 1.5% and a resulting HF concentration of 14 parts per million, right? So 14 versus 13 parts per million shows fairly good agreement. So again, that was done. I did also want to briefly mention some of the German government testing that was done. So again, this was done by the German Road Transportation Agency. And essentially they took vehicles and used a dynamo to heat up the manifold to 700C. They then used pre-damaged parts taken from other collisions and released the refrigerant through those damaged parts and then measured the HF. The key takeaway here is that in most cases, there was no ignition and HF was below 1 part per million. There were 2 cases of actual fires. And in both of those cases, the time-weighted average concentration of HF was 75 and 85 parts per million. Those again would be below the acute guideline exposure limit of 95. And the German agency actually considered these 2 situations unrealistic, things that would be very unlikely to occur. And so they overall concluded that 1234YF was safe for use in foreseeable applications. Next slide. So all of this information came together in a number of risk assessments that really then looked at potentials for both refrigerant ignition and HF exposure. And this has been done for a number of refrigerants, not only 1234YF, but also 2 HFO containing blends, and most recently for 152A in a dual loop system. And in all of these risk assessments, the risks of HF exposure have been estimated to be quite low. And really less than what would be kind of an industry standard. So the industry standard may be 1 per million operating hours, and that is 10 to the minus 6. And we were several orders of magnitude below that level. So again, not really indicating a significant risk once all of the potential requirements for an exposure were actually taken into account. Now, no comparable risk assessments have been done for the stationary sector. However, a number of tests have been done that could then be useful in a risk assessment. So, for example, studies have been done looking at hot surface ignition temperatures. Studies have also been done looking at different ignition sources that might be relevant to the stationary sector. So things like toasters and hair dryers and vacuum cleaners and light switches have all been looked at. And most of those have been found not to ignite these refrigerants. In addition, some consequence studies are actually being done. So actual field sort of studies where refrigerants are being ignited and sort of seeing what the impact of those ignition events would be in terms of flame spread. So a lot of work is being done to sort of get ready to do some of this risk assessment work. Next slide. So I did just want to mention also regarding the automotive work that both the European Joint Research Center, which is kind of the chief technical body of the EU, as well as the US EPA reviewed those risk assessments, particularly the 1234 YF risk assessment, and approved them for safe, as being safe for use in automotive vehicles. So, you know, it's not just the folks making or sort of implementing the refrigerants, but also the regulatory bodies that have really given this a stamp of approval. Next slide. So what are the next steps for ASHRAE 1855? So again, we're responding to initial ASHRAE feedback on the report. I actually have a sort of revised draft sitting in my desk that I'm going to look at after this call and then send off to ASHRAE. So we're definitely, you know, nearing the end of this. We are developing a list of conclusions and data gaps. I mean, I think there are some very useful learnings that we can get, but also a number of data gaps that will be identified. And then as part of the study, as Steve suggested, we'll be suggesting some possible follow-up studies to address some of those data gaps. Next slide. So I just wanted to, again, sort of leave you with this idea that, you know, there is no risk of HF generation or exposure under normal operating conditions. It's only when we have some sort of accidental situation. And even there, again, this is kind of the idea of the risk assessment. There are a number of things that have to happen for there to actually be an exposure. So, you know, you need to have a leak. The leak has to be large enough to release enough refrigerant. A small corrosion leak may not do it, will not do it. The leak has to be sort of in the right place and direction. It has to be directed towards an ignition source. You need an ignition source present at the right time. It can't occur well after the leak or before the leak. It has to occur when the leak actually happens. The hot surface or the ignition source has to be powerful enough, right? It has to be hot enough or enough energy. Many of these refrigerants have very high minimum ignition energies. And then nothing can occur to reduce the refrigerant or the HF concentration, right? You can't have blowing air that might spread things out. And finally, a person has to be present to actually be exposed. So there are a number of things that need to occur for there to actually be an adverse effect. So again, rare, accidental, and acute exposures. And again, just to sort of emphasize the point that Mary has made, all fluorocarbons really have the potential to generate some of these compounds. It's really a risk. It's really a question of frequency and magnitude rather than a new risk altogether. So with that, I want to thank you for your time, and I'll turn it over to the next speaker.
Thank you very much, Tom. Now we're going to move to George. Thank you, George, for talking through the next project.
Okay, go ahead to the next slide. What we're looking at is firefighter concerns with A1 versus A2L refrigerants relative to heat and gases generated, because firefighters show up on the scene when something bad has already happened, and quite often there's more than one thing that goes wrong. So they're concerned about potentials for flash or explosion hazards, and the influence of fire dynamics from refrigerant leaking during their suppression and overhaul activities. Okay, next slide. Again, similar firefighter concerns have been brought up about battery energy storage systems. There's been a number of incidents in the field of explosions in these large storage systems. Similar with photovoltaic on rooftops can change the fire dynamics of the roofing materials, and lightweight constructions of particularly glue laminated joists can delaminate during fire construction. So what we're looking at is to facilitate acceptance of these refrigerants in society. Again, the bottom line there is the test parameter has been selected to provide a knowledge and data for the fire service to adapt their tactical plans for fire events involving A2Ls. Next slide. So we want to demonstrate through fire scenarios that hazards may be encountered, or test the hazards that may be encountered when it involves A2Ls as compared to A1, and develop educational materials for the fire service for their considerations. And once the project is finished, that information will be published and available to fire service organizations. Next slide. So we originally were looking at 5 demonstration scenarios. That's been narrowed down to 4. The bottom one we're not going to be doing in this project. We want to look at comparing A1 and A2L refrigerants relative to heat and gases generated in an open flame. I'll talk about each one of these a little more. The next one is, thank you. We want to look at hazards during suppression, where we have a compartment fire and we're trying to knock down whatever remaining fires, and perhaps a leak occurs during those. And actually, that's the bottom, the 4th one on the list. The other 2 in the middle is looking at a compartment fire that's ventilation limited, and then a leak occurs into that hot gas layer. And what effect does that have on firefighters perhaps approaching the fire room from a hallway? What might there be exposures? The 3rd one is where we actually have a compartment fire with an installed AC system, and what may happen to that system as far as leaking into that. Next slide, please. Again, I'm just showing the compounds. You can see the A1 all contain fluoride. The A2Ls contain it. There is 1/4 refrigerant we're going to test, R466A, which actually contains fluorine and an iodine compound. Next slide, please. So what are we looking at? We're looking at refrigerant flow rate, the heat release rate that's going to come out, what temperatures develop, what ventilation flows occur, what's the heat flux that might be exposed, the gases, oxygen, CO, CO2, and acid gases. And if there is any room overpressure, we want to monitor that as well. We'll be doing thermal imaging and video. Next slide, please. So this is our first scenario, and I've kind of overlaid two photos here for relative size. We're going to be discharging refrigerant under a calorimeter hood into an open flame, and then we'll be measuring the heat release rate, whether it's complete or partial combustion. We'll also be measuring the acid gas samples immediately over the fire, because we're concerned if we waited too far, any acid gases may be reacting with the hood materials inducting itself. So we may not get good mixing for a complete estimate of how much HF was generated, but we'll certainly have relative comparisons of here's an A1 and what we saw, and here's an A2L and what we saw in those cases. So we should come up with some relative comparisons, and we may be able to make some estimates of absolute concentrations, but there'd be a considerable measurement error on doing something like that. Next slide. This is the compartment fires. In scenario 3, we'll have a complete AC system installed in the compartment room. We'll have several ignition sources there. These will actually be commodity class 2 sources of ignitions, cardboard boxes packed with plastic cups. So we're inspecting a fairly sizable fire. We'll have, we'll have HF collection points. We're also going to be measuring temperatures, room overpressure. So at some point in this fire, as it develops, we'll be releasing a leak into this developed fire. In the case of an installed refrigerant system, we're just going to see if a leak actually develops, because there will be copper tubing in the overhead. The temperatures are going to be high enough to significantly reduce the yield temperature of copper. So it's possible there might be a split occur in those. It's possible it may occur in the aluminum A coil inside the AC system. So next slide, please. This is the scenario where we're looking at an overhaul condition. So we'll have a couple of fires simulating something that needs to be knocked down. Firefighters are present, and then a leak occurs with active fires in the room. What is the exposure to a firefighter? So you'll see that we have several acid gas locations, thermocouples, and I guess, again, the room overpressure. I did want to say that in the first scenario where we're spraying frame, we're using the R466A in that scenario. The other scenarios, we're using R410A, which is an A1 refrigerant, and then R32 and R454B, which are both A2L refrigerants. So next slide. Okay, I guess next speaker.
Thank you very much, George. We really appreciate that update. Now we just wanted to, respond to a couple of questions from participants. Mary, I'm going to start with you. There were a couple of questions around some of the details of the hot surface ignition testing that you had talked about. One question was, is the HSIT a function of pressure? So
yeah, no problem. Listen, we, HSIT and AIT are both done ambient pressure, and we've never pressurized the systems. It's really something that we're looking at. For HSIT, we're looking for refrigerant to leak out of a system and onto a hot surface that's near, beside, or in a ductwork. So you can envision that that's not under any kind of pressure situation.
Thank you so much, Mary. Sure. One of the other questions that we had was, there was a question around what temperature does fluorine start to pull away from the refrigerant compounds? If you have any more details around that.
Sure. In general, we see that around 300 to 400 degrees C can potentially knock off a fluorine atom. I think, though, that's where we say it starts to happen. What I think all the literature and everything is pointing towards is that it's much higher temperatures that people are really starting to look at HF levels. So I would put that in perspective. That's all.
That's great. Thank you so much, Mary. Appreciate that. And then we've also had a question. Now, this is a little bit more complicated question, so if you could bear with me. When hot surface ignition temperature method of test were developed, was the design of the planchet made in consideration of the refrigerant gas release flow rate, considering some relevant non-dimensional ratios?
No. So take that first part there. I'm going to say no. I really appreciate this question line. I read it. I'm very excited about it. I wish this person and I could get together and work on it. No, I would say actually what this was is it was looking at, I showed you guys the the flat plate that was done by Honeywell, the heating unit that was done at Exponent under the SAE CRP, and then the manifold that was done by Interest. So our hot surface testing was done more to just start with the flat plate test and come up with something from there. But we always envisioned this as being a multi-generational project. And I think Dick Lord did some great work by adding heating elements and more dynamics to the test. So we envision there being a part 2 and a part 3 and expanding that test. So that's the first part of the question, Helen. Next part.
Thanks. Yeah, and the next part. This person wants to better understand the extent to which the method of test is valid when seeing the sharp drop in planchet temperature. For example, does the temperature drop vary from the refrigerant to refrigerant based on density, specific heat, and thermal conductivity?
Yes, we've investigated. So let me say this. As much as I can say in this form, I would say yes, our testing indicates that, but do I have enough data to go forward to make a statistical difference in the refrigerants? I would say no, we're not there yet. So for this form, I would say yes, we are aware of that, and we think there could be some opportunity to go and look at you know, differences in the actual refrigerant and the density and all that. But right now, I would say the test is more macro, and we don't have enough definition to get into those levels.
Okay, great. Thank you, Mary. Really
Sure.
appreciate that. You can tell that we have all sorts of variety of folks on this call, some with very little technical expertise and some with a great deal of technical expertise. So one of the questions here is around the focus on the automobile industry. While while we are working toward a transition for the air conditioning industry, including different sizes of charges. And I would answer that, there's a lot that we have learned through by standing on the shoulders of giants, all the work that was done for the automotive industry. A great deal of study has taken place. As you know, and Tom, I'm going to ask you maybe to talk a little bit about this here in a minute. You had kind of talked about, the risk really is if we have, some very serious conditions occur, the normal operation, we shouldn't see that sort of thing. So Tom, could you talk a little bit about that? And I don't mean to put you on the spot, but if you could also talk a little bit about how you see the information that you learned in your review of the available data and how that might be of value to the air conditioning industry.
Yeah, sure. Happy to. I mean, I think it's a valid question. And, certainly from my perspective, I don't think we're going to try to take the automotive results and just sort of plop them and say, there you go, everything's fine for the stationary sector. I mean, I think, there are different things that have to be considered. But I also think that, gosh, there was, I think you were suggesting, Helen, there was so much work done for the automotive side, and it makes sense to use that as our starting point and then build from there. And certainly, there were a number of kind of fundamental learnings, I guess, from that automotive work that would be, that would be useful, right? From the automotive side and from the stationary side, I mean, I think, again, it's a matter of risk assessment and really trying to understand what all the potential mitigating and exacerbating factors that might occur. And certainly, charge size would be one of those things. The room situation would be another. And so, we would want to do a risk assessment where those factors were all considered and accounted for. So, I know that there have been CFD modeling studies, right, and sort of measurement studies looking at dispersion of the refrigerant after a release and where a flammable concentration would occur relative to where a leak might occur. So, I mean, I think there's been a lot that has been done and can be done to look at the stationary side and put those risk numbers into perspective. And, as we showed on that chart, there are a number of things that need to be considered, and all of those can be considered in the context of a stationary sector specific risk assessment. So hopefully that's a helpful answer.
I think that it is, Tom. Thank you very much. Really appreciate that. George, I've got a question for you. There's a member of one of the participants that wants to know how the fire load of scenarios 2 and 3 compare to typical types of structure fires. From an order of magnitude perspective, is it lower or the same or higher than a fire in a residential home or office setting or other context? We just wanted to get, I don't know if you know the answer to that. If you don't, we can certainly answer it offline, but if you have any feel for that, there's somebody out there that'd like to better understand that.
Sure, I can explain that. What we're looking at is a compartment fire that is ventilation limited. So just about any residential home with a normal amount of furniture can create fires that are ventilation limited, meaning the size of the fire in a confined compartment is limited by how much air can actually get into the fire. So we wanted to make sure that we had enough load in this room so that it actually becomes limited by the amount of air that comes in low in the room and the hot gases leaving out the top of the room. So yes, it is a larger fire load, but we wanted to make sure that we're in a ventilation limited condition.
Thank you very much, George. I've got one more question here, Tom, for you. Could you talk a little bit about the risk assessment that was completed for AHRI for air conditioning in 2011? I know that we don't have, obviously, we probably need another hour to really talk about it in detail, but could you just describe what the, kind of the scope of what that was? I know that was not, it didn't include, specifically HF generation, but it looked at some other things. Could you share a little bit of that with us, please?
Yeah, well, yes, I could share a lot, but you're right, we don't have time. So yeah, I mean, I think essentially what we did was we looked at, again, all of the potential factors that could sort of be related to a refrigerant release from an, AC, sort of a heat pump system in different locations, right? Different settings within a house. Used all of those various values, including some CFD modeling of concentration in a fault tree analysis where we basically looked at the impact of all those factors, one relative to another. So again, that was kind of a way of bringing all that information together to address some of those concerns the prior question sort of alluded to, right? So what things are specific about a stationary development or application that we need to consider, and that the risk assessment, the fault tree analysis kind of brought all those things together in the context of what the actual risk estimate would be.
Great, thank you so much, Tom. And Judon, if you could go back one slide, I asked Tom if he would kind of wrap up for us, but before he does, first I wanted to thank everybody for participating. I'm sorry we didn't get to all the questions. I do see a few more here. We will send you an email with the response, because I think that these are important questions, so we won't forget about these. And Tom, also I want like to thank everybody for participating. You are among more than 1,500 people that have participated in these webinars. So clearly a lot of interest in these, and we will certainly be looking at doing some more of these. So if you want to send your comments to us around other things that you're interested in hearing more about, we will be looking for opportunities in the future to do some of that. And Tom, could you just wrap up for us and just kind of remind us of the important points to remember around what you learned in your research?
Sure. I mean, I think, these are things that, are sort of common to all the various projects. Again, not a conclusion of the report because the conclusions aren't available yet. But I mean, I think just sort of general ideas, that there is no risk of HF generation or exposure under normal operating conditions. I mean, these refrigerants are stable. It's not as though HF is present, inside the system or is going to be released during normal operation. It is really some accidental situation where we might have a potential exposure. And even there, it's only going to be when we have this, alignment of various factors, again, that would be addressed in a risk assessment that are such that a person is able to be exposed, as a result of a release. So again, a number of things have to be required, and each of those has their own probability of happening. So, you might expect the probabilities to be, to be reasonably low, again, depending on what the factors are. So we're really talking about rare, accidental, and acute exposures. And these are not novel risks. These are things related to all fluorocarbons. It's just, again, a matter of degree and frequency. It's also important to note that there are other highly irritating and toxic gases that would be potentially released. For example, in a fire, I mean, you've got other chemicals present, other products present that might, produce other adverse chemicals as well, things like carbon monoxide or HCl. So again, those things need to be considered. But always, a kind of final message is that PPE and best maintenance practices should always be used to minimize and eliminate exposure to all refrigerants and their potential combustion products.
Thank you so much, Tom, and thank you to all of our speakers for this series and for all the webinar series, and also to all of you participating in these discussions. We greatly appreciate that, and we look forward to talking with you again. We hope you all stay safe and healthy in this pandemic and we look forward to seeing you again in person, hopefully one day soon.